All right, let's just continue. So we have introduced complex gates, we have introduced multiplexers, XOR gates. These are handy little gates that we will be often using. Before leaving this subject, what I want to do last is the following. Remember, in the number system, we talked about an overflow circuit. We said an overflow circuit is a circuit that takes an adder and looks at the sign bits of the adder. Okay, the sign bits of the adder. Like this is a sign bit, this is a sign bit, and then looks at the sign bit of the result, which is S. If it finds that, for example, the inputs are 0, 0, the output is 1, that means the inputs are positive, the output is negative, that's a bad case, it's an overflow. I'm not saying what to do about it, I'm just saying, well, this is no good. The 8-bit is not enough. So that's an overflow circuit. And that's an overflow case, and I'm detecting this, okay, with a circuit that I'm calling it overflow. Alternatively, if I have a 1 here, I have a 1 here for the A7 or the sign bits of A and B, and I have a 0 for the sign bit of the result. That again is an overflow because two negatives cannot be a positive when added. So what I like to do is to build a circuit called overflow detector. Okay? And with what we have already seen, we can do this. The overflow is this. Let's read this. If A is 1, B is 1. Now, I'm saying capital B representing the sign bit, or B7. Capital A is A7 and capital S is S7. So if I'm saying if A is 1, B is 1, S is 0, that's the red case I'm showing up there. That is a case of overflow. Alternatively, if A is 0, see the blue up there, B is 0, and S is 1, then that's again overflow. So what's overflow? Either the blue or the red. And therefore my expression becomes what I'm showing over here. This is going to be my first design using transistors, using gates. I'm going to build this circuit. With what we have already seen, this is not very difficult to build. Okay, let's just translate what I'm showing in this expression to gate structures. Let's look at the red part first. The red part says S bar AB. That's not red. The red part says complement of S AB, which is this. The blue part says complement of A, complement of B, and then ORed together. Okay, complement of A, complement of B, and S, ANDed together. So I have these two structures, and then what is happening to these two structures? Well, these two structures are being ORed together. Remember when I said my sentence, I said if A is 0 and here, if A is 0 and B is 0, okay? If A is 0 and B is 0 and S is 1, that's a case of overflow, okay? Another case of overflow is if A is 1, B is 1, S is 0, that's another case of overflow. What is the overflow? Either the red or the blue. And therefore, I say either the red or the blue. And then this is the word "or" that I'm using. I'm saying either the red or the blue. That's an overflow. I just built an overflow detector circuit. Now, you want to build it? Well, you can have ands and ors. You can have you can build this using complex gate structure. You can build this using regular gates. Nevertheless, I was able to turn this into transistors. Okay, so if you ask me, can you do a overflow circuit? Sure, I can. I can turn it into transistors. And so let's look at building this. I have ANDing, I have ORing, but see, I'm not going to do complex gate for now. I'm going to do the primitives I have. Remember, I can easily have inverters. I showed you a transistor up there, a transistor down below, that's it. So this is structure, my transistors are done. My inverters are done with. Okay, what else I have here? I have a 3-input AND gate. Well, I recall I don't have an AND gate. I have an AND gate, not an AND gate. So what I can do is to have an AND instead of the AND, okay? And then get this done. But then I have the complementing. Remember something. Remember that, let's look down below what I've shown you here. Remember this. When I showed you the NAND gate, I also said what the NAND gate, the symbol of the NAND gate, can be either an AND with a bubble or a OR with the bubble inputs. Okay, with bubble inputs. So for these structures, I can use any of these symbols here. Okay, as far as the NOR is concerned, the NOR can be a OR with bubble output or AND with bubble inputs. So let's go back to this structure here and then say that one alternative for building this would be just say, well, I have an AND, so let's put an inverter. I have an AND, let's put an inverter. This becomes AND. This becomes AND. Okay, so that does this. This does this. How about the OR? The OR, I build an OR and put an inverter in front of it, so that's an OR, and therefore I just build this circuit. The problem with this circuit is that I'm using too many transistors. I'm going to do the alternative implementation. The alternative implementation, I'm going to put an AND for this, an AND for this, okay? But then, instead of complementing them, I'm saying, let's take the output of these two NAND gates and NAND them again. If you NAND them again, what happens is instead of drawing the NAND symbol, you're going to, instead of drawing this NAND symbol, you're going to be drawing this NAND symbol. So I put a NAND here, a real NAND, I don't complement the output. A real NAND, I don't complement the output. And then I put a real NAND here, I don't complement nothing. I don't complement the output of it. But this NAND is represented as an OR with bubbles. Now let's read this circuit on the right hand side. I have an ANDing with a bubble connected to an ORing with a bubble input. These bubbles cancel them out. The two bubbles below also cancel out. And therefore, logically, this is an AND OR circuit, even though I'm only using NANDs. Let's do some counting, and I'm going to count the number of transistors here. I have 6 here, 6 here, 2 here, 2 here, 4 here, 2 here, 2, 2, 2, and therefore I have 8, 16, 20, 22, 24, 26, 28 transistors. Let's look at the right hand side. an AND with 3 inputs, an AND with 2 inputs has 2 below, 2 up. Here becomes 3 below, 3 up, and therefore 6 here. 6 here. 4 here, 2, 2, 2, and therefore I have 12, 16, 22 transistors. By just using the proper notation, if I were to turn this into a transistor circuit, I would be saving 6 transistors using the same exact implementing the same exact function. Not only that, the circuit on the left hand side is a slow circuit because I have NAND gates going into inverters, going into NOR gate, going into inverter, 4 layers of logic, and therefore I will have 4 logics forming my worst case delay. Let's do the overflow circuit, this time in Verilog. The inputs are A, B, and S. And then I have the overflow V output. And what I have, let's do this. I have wire AI, BI, SI, and then JK. So what we have is inverted A. This is inverted A. Here. Okay, this is a NOT gate. Instead of writing 3 NOTs, I'm saying NOT, this, and then comma, this, comma, this. I could, instead of comma, put semicolon and then repeat the not sharp sign 5. Okay, but then I'm putting all of these together. So AI, BI, and SI become the complements of A, B, and S. Okay, and then here is the AND gate, taking the complement of A, AI, complement of B, BI. Okay. And then the S input forming the J down below is another AND gate, and that is A. Okay, another A, B, SI, that is giving me K, and then notice that the OR gate here is J and K ORed together. Okay, and that's my overflow circuit as described here. And this is AI, BI, and this is SI, JK, and this is the overflow circuit. All right, so what do we have here? We have the overflow circuit in terms of AND, OR, and NOT primitives. Okay. Something I could do just so that you know that line 5 puts 3 inverters without saying not this, not this, not this. Okay, just kind of factoring out not comma, not 5. You could do the same thing by changing this semicolon to a comma and then crossing this. What it would mean would be and one of them is A1, one of them is A2. The first AND is the preparing output J, the second AND output K. You could do either one, however you want. I have to say something more about this, and notice that intentionally I put my OR first. Okay, the reason is it doesn't matter which one comes first. You want to put your ANDs first, fine. this is a concurrent body of Verilog, means the order of the statements does not make any difference whatsoever. And yeah, I just covered this entire thing. I'm gonna write it on this right hand side, on this left hand side. Instead of putting all of these together, I could just look at the numbers here: 15 for NAND, the 10 for the OR, and then 5 for the NOT, and that would be 30. 30 nanoseconds, and I guess I'm using 40 there. Instead of this entire thing, I could just say assign, okay, and give it some delay, whatever. Let's say the worst case of that, and then say V is, just write down the expression we had, tilde A, tilde A, tilde B, and S ORed with A and B and tilde S. Okay, and then put some delay to account for the entire thing. So what we have done so far is we have shown you the Verilog at the transistor level, at the gate level, and also at the assign level, at the expression level. We are showing that at the transistor level, you're going to get a lot of details, but then there is a long simulation time. At the gate level, you're going to get not as much delay, not as much precision, but then not as fast as, not as slow as the transistor level. At the higher level we have shown so far is assign. This is the fastest, only one expression is being evaluated, but then you are lumping all the delays together. For example, 30 or 40 nanosecond delay you're using over here. And when you go from one level to the upper level, what you got to do is to come up with the worst case delay. To test this, I generate a test bench for it. Okay, continuing on our Verilog overflow test bench, and for the test bench you do this. Okay, so this is the circuit, whichever you want to do, whether the assign or the transistor or the gate you want to do. You have an A, you have a B, and you have an S, and you have a V output. Okay, I create 3 signals or 3 wires, let's say AA, that I will connect to A, BB, that I will connect to B, and SS, that I will connect to S, and the VV, that I will connect to V. Okay, in my test bench. And those that are connected to the inputs, like AA, BB, SS, these are declared as reg. This is what Verilog requires. It says that if you want to put some value into something and it's an input, then declare it as reg. So I declare it as reg. I initialize the AABB's SS reg as 0. Okay, so initially it's 0. VV is a wire. Okay, VV is a wire. Since it is a wire, since it is connected to an output, it is a wire. I'm not putting a value on it. I'm reading a value from it. So this first part declared my ports connected to this. The second part is instantiating my overflow circuit. Instantiating my overflow circuit, meaning that that circuit that I'm testing, which is OV, remember, it is OV here. It is OV, and the ports are A, B, S, V in this order. I instantiate it, and then in that same order, I connect the AA, BB, SS, VV to the ports of that. So AA, which is declared here, the red one, connects to the first port, becomes A, BB to the second port, SS to the third port, and so on. This is done. This is the third part of the this is the second part of the test bench. The third part of the test bench is assigning values, which is this. Okay, in the initial block, which is what this is called, in the initial block, instead of concurrent statements, what I have is procedural statements. Let's read this. It says, wait for 73 nanoseconds. Why 73 nanoseconds? Because of this time scale on top, which is saying nanosecond. Wait for 73 nanoseconds. BB was 0. Now, after 73 nanoseconds, change BB to 1. Wait 97 nanoseconds after that, change SS to 1. 67 nanoseconds, and then BB to 0. Just play with it. Just put values in it. And then at the end, wait 121 nanoseconds, and then stop. Okay? And so what I'm really doing, I'm putting some waveform on the inputs, and I simulate this, and then you will be seeing that the simulation result is going to give you this. This shows that several cases, one is this one here, and one is this one here, I am getting overflow. And notice the important thing here, that my overflow output is happening after a delay. Look at the VV output. It happens after a delay when AA is 0, BB is 0, and SS is 1. Okay, this situation doesn't happen immediately, it happens after a delay. The same thing over here. Notice that as soon as SS becomes 0, there is a delay between the time SS becomes 0 and VV becoming 1. And that is the delay that we put in our description, which is this description here. All right, we are done, and we have covered these topics: event-based simulation, concurrent simulation, transistor structures, timing of them, how to build primitive gates, how to describe primitive gates, gate delay and timing. We talked about timing, TPHL, TPLH, and so on. We talked about complex gates, and then we took a little example using transistors or gates or whatever, generated a test bench, and that was the overflow circuit that we developed back in the previous topic, which was on number systems. All right, this is done, and then we go up into expressions and Boolean algebra and logic circuits. No more transistors.